Let's discuss what are called radical functions. Now, radical functions are also known as, aka, root functions. You'll hear different authors refer to either radical functions or root functions, like, for example, the square root function. Let's get an idea of how to graph radical functions and find their domain in the range as well. So let's graph f of x is equal to the square root of x plus 3, and we're asked to find the domain in the range. Now, whenever you meet a new function, it's always a good idea to create a table of values. Let's do that here. I'm going to create a table of values. So the way you create a table is you pick different x's and figure out find the corresponding y's for those given x's that you choose. So for example, looking at this table, how about I pick x to be, let's say, 1. So when x is 1, the question is, what do I get for y? Let's see. F of 1 is equal to the square root of 1 plus 3, which is the square root of 4, which is equal to 2. So when I plug in 1, the output is 2. Now, you can see that 1 was chosen sort of strategically, and the reason is because whatever you plug in here, you have to add 3 to that, and then take the square root, right? And 1 was a good choice because 1 plus 3 is 4, and 4 is a perfect square, so that when I take the square root of that, I get a whole number. So, in other words, something like, like 2 would not be that good of a choice for x, because when you plug in 2, well, you get the square root of 2 plus 3, which is the square root of 5. And the square root of 5 is not a whole number. It's an irrational number. So the problem with that is that it makes it difficult to graph. And likewise, if you pick something like, let's say, 0, right? Even though it's simple as far as x is concerned, for y it's not so easy because 0 plus 3 is 3, and the square root of 3 is, if you write in the square root of 3, that's about equal to 1.7. Okay, it doesn't make it easy for graphing. So I'm choosing x to be sort of strategic here. What would be another good choice for x? Well, 1 gave rise to 4 right here, right? The next perfect square I'm thinking about might be, well, 4, and then how about 9? So if x is 6, that's a pretty good choice because 6 plus 3 is 9, and the square root of 9 is 3. Okay? Now, the only problem with that choice is that 6 is getting fairly large, so that's going a little bit too far on the x-axis. So if we sort of reverse our strategy and think of perfect squares that are smaller, how about we choose a value of x to be like -2? Now you might say, wait a minute, you can't choose a negative for x because it involves the square root. That's true. This does involve the square root, but watch what happens when you take -2. So when you plug in -2, you don't take the square root of -2. You take the square root of -2 plus 3. And that's the square root of 1, which is 1. So when I plug in -2, I get 1. And then finally, if you plug in -3, what happens? Well, -3 plus 3 is 0, and square root of 0 is 0. So if I write that out, f of -3 is the square root of 0, right? Because -3 plus 3 is 0. And then the square root of 0 is 0. So -3 is actually a good choice for x. What happens if you pick -4 for x? Well, if you do that, -4 plus 3 is -1, right? So f of -4, that's equal to the square root of -4 plus 3, and that's equal to the square root of -1. But the square root of -1 is not a real number, so this is not real. So in other words, we're just interested in what are called real valued functions. We don't want functions that involve the square roots of negatives. So what that means is that we're not going to choose any number less than -3. So if I plot the values I have so far, 1, 2, 6, 3, -2, 1, and -3, 0, let's do that. So 1, 2 would be right about there. And then 6, 3 maybe over here. Lining those up. -2, +1, so like so. And -3, 0, like that. And if you plot more and more points, what you're going to find is that you end up plotting more and more points along this curve. Now, it's not a line. It curves in pretty sharply right there. So if you get more and more points, you get a graph. Let's go ahead and graph that in now. And this would be our graph. Now you can see that that graph looks like it's not a line, right? It's basically half of a parabola but on its side. And that's how square root functions always look, like half of parabolas but on their sides. Now, a couple things. First of all, the domain and the range, right? We know how to find the domain and range from previous videos, and if you need to go back and review that, now would be a good time. So the domain, you think along the x-axis. So I can see that, if this was like a thermometer, I could see the temperature could go down to -3, but then it gets infinitely large. So the domain is -3 to infinity, and the range, right? We play the same game, but now think along the y-axis. And if this was a thermometer, the lowest temperature would be 0, right, on the y-axis, all the way up to infinity. So the range is from 0 to infinity. Now, that's a 0, not an, looks like an 8, but it's not. Let's fix that. So 0 to infinity. Now, it turns out you can find the domain simply by looking at the function. So the function, let me write it down here, it's the square root of x plus 3. Now, anytime you have an even index, right, like a 2 for a square root, or a 4th root, or a 6th root, and you're dealing with a function, whatever is here, whatever's under the radical, that is the radicand, that always has to be positive or equal to 0. So that has got to be greater than or equal to 0. So you can write that condition right away. You can say, whatever's under the radical has got to be greater than or equal to 0. And you can write that inequality. And when you do that, when you solve that inequality, that is by subtracting 3 from both sides, you get x is greater than or equal to -3. And that is a restriction on the domain, right? Whatever you plug in has got to be greater than or equal to -3. And I can see that on my graph, right? I can't plug in an x less than -3. So this actually gives you the domain right away. -3 to infinity, those are the set of numbers satisfying this inequality. And we find the range by simply looking at the graph. Okay, let's take another radical function. This is, by the way, called the square root function. Let's take another one. So this would be called a cube root function, or generally a radical function. So the difference here, of course, is that the index is a 3. And let's create a table of values, just like we did for the square root function. So again, we pick x's and figure out what the corresponding y's are. But now you want to pick x's, well, once again, strategically, but you want to pick numbers that are perfect cubes, right? Like, for example, 0 would be a good choice because the cube root of 0 is 0, but then when you subtract 2 from that, you get -2. And if you plug in 1, the cube root of 1 is 1. Subtract 2 is -1. Plug in, well, 2 would not be a great choice, right? Because the cube root of 2, that's difficult to find out. It's not a rational number. What's another perfect cube? How about 8? Right? It's a pretty large number, but it's a perfect cube. And the cube root of 8 is 2, and 2 take away 2 is 0. Let me just go ahead and show you how to write that. F of 8, that would be the cube root of 8, take away 2, which is, well, the cube root of 8 is 2, and then take away the 2 that's already there, and we get 0. Now, it turns out you can plug in numbers that are negative as well, right? Because there's no restriction when you're taking the cube root of a number. Only when you're taking even roots of a number are you, do you have to watch out for what you plug in. So I can plug in -1, for example, and if I do that, the cube root of -1 is -1. Take away 2, I get -3. And if I plug in -8, for example, I get -2, right? Cube root of -8, let's write that out. Plug in -8, I get the cube root of -8. And then if I subtract 2 from that, I get -2, take away 2, which is -4. So I get -4. And we could keep playing that same game. Now, let's go ahead and plot the points that we have so far. So 0, -2, that would be right here. 1, -1. 8, 0, way out there. -1, -3, like so. And -8, -4, so -8, -4, right? So maybe out here. And when you plot more and more points, you find points that lie along this curve, like so. It goes like this, but then it kind of does this like little S shape right there. It goes like S shape, and then it continues on like that. So the graph is going to look something like that. Let's go ahead and plot that in, or graph that in now. And that would be our graph. It's basically sort of this curving in, and momentarily it's vertical. That is, it's vertical just at one point right there. So it's coming in like this, barely, just momentarily vertical, and then it basically follows this shape just inverted like so. So it's getting larger and larger, but just kind of doing this S shape in both directions. And the domain for this function, so the domain, well, you can plug in whatever you want, right? So it's going to be negative infinity to infinity. And the reason is because you have the cube root and there are no restrictions when the index is odd. And I can see that the range, likewise, is going to be negative infinity to infinity. That is, we can expect every number to occur as an output for this function. Okay, so those are the basic shapes for square root and cube root functions and how to find their domain and range. Until next time.